Hey everyone, this physics video is still under the number 3 because we're learning how to go about solving second law scenarios, okay? In fact, there's going to be a D.3c looking at another particular scenario with forces at different angles. So in this video, after we learned the basic ideas of Newton's second law, let's look at the general strategy for how to solve a problem utilizing this second law, all right? So there's a list. These are the things that you should try and keep track of, things you should do, whether explicitly and obviously on, say, a piece of paper, or at least have in your mind. Now, depending on your teacher, you might be required to do some of these things, but whether you're required or not, all of them are good strategies, okay? This is how we're going to approach problems with Newton's second law. Number 1. We're going to draw a free body diagram for our objects. This is normally, whether again or not, you're told to or not, this is the best thing to do because Newton's second law is all about understanding forces and the total number of forces in the direction they act. Free body diagrams show us how to draw and how to recognize the forces that exist and their direction. So we'll draw free body diagrams for every scenario. We will label what directions we're choosing are positive and negative. Remember, maybe something like this will pop up, where here I am kind of declaring that the right is the positive direction for me and upwards is positive. Technically, you could choose whichever direction you want, but conventionally, right is positive and upwards is positive. Okay? After that, now we know what forces are acting on an object. We know whether or not to label them as positive or negative. We can set up Newton's second law, the sum of the forces. Remember, the sum of the forces equaling mass times acceleration. Because vectors have to be completed separately, the perpendicular vectors at least, we're going to do that for horizontal forces as well as vertical forces. So we'll do this twice, once in the horizontal direction and once in the vertical, or at least, it depends on the question. If all the forces in a question are just acting up or down, well, we would look at the sum of the forces, up or down, okay? The next thing, number 4 might introduce a word that you're unfamiliar with. Okay? It says, consider if the object is accelerating or in equilibrium. First, you might not know, but a lot of problems will tell you, or at least hint, they'll say something like the object is accelerating, or it'll ask you, calculate the acceleration of the object. It also might say that the object is at rest, or maybe the object is at a constant velocity. Maybe it's moving at a constant 5 meters per second north, a constant velocity. Both of these things are examples of non-acceleration, right? Because when you're accelerating, your velocity is changing over time. And we know, both from the second law and from Newton's first law, in fact, that if you're not accelerating, the net force is 0. This is known as being in equilibrium. The word equal here has to do with the idea that forces are equal. They're balancing out. They're canceling out. If it says objects are in equilibrium, or if it tells you an object is at rest or it's moving at a constant velocity, the acceleration is, of course, 0. So when we set up the sum of the forces, it actually might make our lives a little easier because the sum of the forces equals mass times acceleration. But if one of those is 0, it would mean that the sum of the forces adds up to be 0, right? Because A is 0 and mass times 0 is 0. Okay? So maybe look out for this word, or just recognize we might be given some helpful information if an object is at rest or constant velocity might tell us how to approach these problems. And then, of course, after we have something set up, we're going to do some algebra. Now, this topic is difficult because often we're creating these equations from scratch. We're not just given an equation to use for every scenario. We have to figure it out. These steps, it's what allows us to figure out these equations to ultimately do step 5 using some algebra in order to solve. Okay? So that's the strategy. Of course, we learn best by doing. So let's get into it. Let's chop some onions. All right, let's apply this strategy to, well, Newton's second law. Here's the example problem I have. It says a student pushes straight down on their 1.6 kilogram physics textbook. So it gives me the mass, m, of the physics textbook. And it says that we're pushing straight down with this force F with a force of 11 newtons. Calculate the normal force acting on the book if, crucial hint, if it remains at rest, okay? Now that's a lot to take in. How do we start? Well, let's go back and think of our set. Number 1 and 2, let's draw a free body diagram and then clearly label our coordinates. So here's my free body diagram. The dot represents the book. Okay? The book is here on Earth, and on Earth there's always weight, and weight always points straight down. Sorry for my lack of ability to draw a straight line. It should be a straight arrow going downwards. That's weight. Well, the table is supplying a support force. I know that because there's no information about like the book crashing to the ground, and it even says, we're trying to calculate the normal force, that support force. So there should be a force. Since the table is horizontal, the normal force should be perpendicular. Nice. Any other forces acting on this book? Doesn't say anything about friction, and the book isn't sliding left or right, so we're not going to worry about friction in this example. Well, of course, the person is pushing down on it, right? It says the person is pushing down with 11 newtons. So I should draw one more downward force, maybe something like this, okay? What should I call that force? What should I label it? I could call it force P for pushing force. This picture has an F, so I'm just going to label it as F. And remember, you could also draw it kind of like this. You could have W and then another downward arrow. Some people draw it that way. I haven't seen that too often. If you make your dot kind of fat enough, maybe you could do this, W and then F. All of those are acceptable. One's not necessarily better than the other, okay? But we'll stick with the one that I originally drew. So there we go. There's my step 1. What's step 2? Let's clearly label my positive direction. We're not really dealing with horizontal motion in this example, so let's just say upwards is positive. And of course, that means that downwards is going to be negative. Next step, number 3. Let's set up the sum of the forces. Again, there's no forces acting horizontally. It's not asking about horizontal acceleration. So let's just do this in the vertical direction, okay? So I'm going to write out the sum of the forces. And this is vertical, and it's important if there was a problem with both types of forces to stay organized. So I'm in fact going to use a little subscript. So what do I do here? The sum of the forces, what does that mean? It means I should literally write out the forces and add them together. But what we need to keep in mind is that these are vectors, so that forces that are acting upwards in the same direction should be added together. Vectors that are acting in the opposite direction, downwards, those might need to be subtracted. So what do? I'm going to add up all the forces, and by Newton's second law, the sum of those forces is equal to ma. The mass of the object times its acceleration. Again, they're vectors, the acceleration in the y direction. Okay, so what forces are acting vertically? Well, there's a normal force. Should the normal force be positive or negative? It should be positive because it's acting in the positive direction. There's also the weight force. Should weight be positive or negative? It should be negative. Remember, these are vectors. Vectors have an amount and a direction. I'm creating an equation based on my free body diagram. It would be wrong if I added these two up. It would imply, reading this equation, that the normal vector force and the weight vector force are in the same direction, and they're not. They're an opposite. And since I'm saying the downward direction is negative, I should use a negative. I'm subtracting it. Lastly, what about this pushing force F? Should I be adding or subtracting it? I should also be subtracting it. It is also acting down. Again, some students ask, why don't I just put plus, 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 and then plug in negative numbers? Well, the physics problem isn't going to give you a positive or negative. Remember, the sign is determined by you. Anybody can choose any direction as positive or negative as they want. And vectors have both sign and direction. If all you're doing is just adding these symbols, it's implying that the vectors are acting in the same direction. And that's not true. So you use pluses and minuses. You add or subtract based on the direction of these forces. Okay? Now, it says the book is at rest. So what is its acceleration? This is an example of the book being, or the object being in equilibrium. So this is actually going to equal 0. So now I have n minus w minus f equals 0. What am I trying to calculate? The normal force. So I'm just going to swing these other two vectors to the other side. Now I'm just doing some algebra. I have n equals, I swing over w, now it's positive. I swing over f, plus f. Okay. What's weight? Remember, weight is equal to mg. All right, it's on the AP Physics 1 equation sheet. It's easy to remember. So it's mg plus f. So the normal force is equal to, it's the mass of the object. The mass is 1.6. G is 9.8. Plus, what's the value of the force? 11. It's 11 newtons of force, plus 11. okay? Now, when I do 1.6 times 9.8, that's almost about 16. It's almost 16, okay? Almost 16 plus 11, I plug it into my calculator. You can check your work. Let me know in the comments if I made a crucial error. But I got around 26.7 newtons, 26.7 newtons. That's it. That's me using Newton's second law to calculate the normal force. One thing, or maybe a couple things before I go. Did you notice I didn't plug in a negative 11 here, even though this 11 was acting down? Why didn't I plug in a negative 11? I already accounted for the fact that the vector is in the negative direction when I wrote the equation. Okay, so now I just plug in the number. When I did algebra, I swung this to the other side. It ended up being positive. But if I plugged in a negative 11, I would get the wrong answer, because then it would imply algebraically that that force was actually helping out the normal force, and it would be subtracting the overall amount. So I already took into account the fact that the force, the applied force, was minus. So don't plug in a minus 11 again. Don't double dip. That would be like, plugging in a negative and then a negative. That gets you a positive. That would give you wrong results. So I already accounted for the negative force. Similarly, this is a little tricky at first. I plugged in regular 9.8. There's a reason in my class, at least, I always put on the board that G equals 9.8 ms squared downward. I already took into account the fact that weight is acting downward. I already did that. In our last unit, we were using pre-made equations from Galileo's contemporaries. So we plugged in a negative sign to account for scenarios with negative accelerations. The original equations, v equals v naught plus at, they were just written for just positive values, and we would have to go in and make changes. But now we are writing the equations. I already took into account the fact that weight is negative. So plugging in a negative 9.8, again, would ultimately get me the wrong answer. So now, since we're creating these equations, you're probably always going to be plugging in 9.8 because you took into account the direction of this force vector when you wrote Newton's second law. That trips students up at first, but remember, negative isn't a rule. It's not a law that G is 9.8. It's that G is 9.8 down. And I already realized, I already took into account, I've said that phrase a lot recently, I've already taken that into account right here. So now we're just going to plug in regular 9.8, okay? Little tough. But there's an example of applying Newton's second law and all the pieces that go with it, all right? We'll be doing a lot of practice with this. Thanks for watching.